Hello people, in this video I will be covering everything you need to know about complex numbers in A-level further maths. So watch till the very end and there won't be anything or you won't get any questions on things that you haven't seen before. We all know that maths, unlike other subjects, is not something you can just learn by watching someone else do it. It's something that you must practice yourself. So this video is meant to be teaching you all the necessary concepts for this topic. I'll release another video titled doing all the different types of questions that you could possibly get for complex numbers. And if you do both these videos, watch them from start to finish. I'm confident that you'll be fine if any complex numbers questions come up, whether it be a topic test, your A-level exam, your mock, whatever. So without wasting any more time, let's get straight into it. What actually is a complex number? You might be thinking, especially if you've never come across this before, we have numbers, we have algebra which uses the x, y, z variables, letters. What's the need for imaginary numbers? But in reality, all of you have come across situations where we do need imaginary numbers. The general explanation behind it is that imagine any positive number, square it. You'll end up with a positive number, right? 2 squared 4, 3 squared 9, so on and so forth. Imagine any negative number, square it. You also get a positive number. So the square operation will always only return positive numbers. But we have the inverse of the square operation, square root, right? So when you square root a positive number, that's not a problem. You get a positive result, right? Because this is perfectly logical, like the square root of 81 would be 9. What happens when you try and square root a negative number? Now, whether it be GCSE or A-level maths, every time you've tried to solve like a quadratic equation, and you've come across this before, where you've tried to square root a negative number, you stopped. Stop the question right there, can't do it, no solutions, move on. But using imaginary numbers, or I in particular, allows us to solve these quadratics that we previously deemed unsolvable, right? And this has applications in theoretical physics and fields like mechanical engineering and so on and so forth, in terms of real world use. So what is I? Let's delve into it through an example. So very basically, x squared equals minus 9. If you saw something like this previously, you just think, no solutions, move on, x can't be anything. This is unsolvable. But let's go through the motions of solving it anyway. X squared is minus 9, then x is plus or minus the square root of negative 9, right? Now, if you're unfamiliar with what I've done in this step, essentially, surds have the special property that the square root of 12 is the same as the square root of 4 times the square root of 3, right? So we can simplify the square root of 12 to be 2 root 3. In a very similar way, square root of 9 or the square root of minus 9 can be rewritten as the square root of 9 times the square root of minus 1. Now, if you notice this minus 1, we've seen it before, right? This is the very thing we defined at the start of complex numbers. So we can solve this equation like we solve any other quadratic equation. Square root 9, get 3, and wherever you see the square root of negative 1, just put 9. So x squared equals minus 9 can be solved to x equals plus or minus 3i. And that's the very basic complex number imaginary number introduction, if you've never seen it before. Now, let's move on to doing some operations. Addition, subtraction, multiplication are really easy. You know the algebraic expressions like x plus 1 or 2x plus 3, how we've been dealing with them throughout GCSE and A-level. Well, luckily, all these skills that you've built up, adding, subtracting, multiplying these, are going to come very much so in handy, because with complex numbers, numbers are written in the form of a plus bi, right? Very similar to x plus 1 almost. You can just add them, subtract them, multiply them, the same as you do algebraic expressions. The only thing you need to look out for is when you multiply I with itself, you're actually doing the square root of minus 1 squared, so it turns into minus 1. So apologies, I squared is minus 1. This is an identity that you must keep in mind. Let's look at an example of this. So if I have two complex numbers, 2 plus I and 5 minus 7i, multiply them both, then just like I would if there were two algebraic expressions, I multiply each term by each other, getting 10 minus 14 plus 5, and the last two terms, this term and this term, will multiply to make minus 7i squared. Now remember, I squared is minus 1, right? So once we evaluate this expression, minus 7 times minus 1 becomes plus 7. This multiplied will give you 17 minus 9i. Now you can slow this down, watch it again, but trust me, don't complicate this stuff. It's the exact same as dealing with algebraic expression. Think of it like this almost. If it was 2 plus x and 5 minus 7x, right? But wherever there's an x squared, you just put a minus 1. Something like that. Now, moving on to some slightly more challenging things. The same way, if you remember in surds, you have the complex conjugate of surd. So for example, if I have a surd which is 1 plus root 2, the complex conjugate of this surd, it's a very fancy word, I know, is just 1 minus root 2. So the same way that you'd rationalize a surd like 1 over a plus the square root of b, rationalizing a surd, all that means is getting rid of the surd in the denominator. Bring all the surds to the numerator so the denominator is just nice numbers. So how you'd accomplish that is that you'd multiply this surd by its complex conjugate. And it will simplify it. As you can see, there's no surds in the denominator here. Similarly, if you're dealing with the inverse complex number, where you have some imaginary number at the bottom, you can apply the very same trick. Just times this by a minus bi, and once you simplify this, you will be left with something that has no complex numbers in the bottom, hence simplifying the expression. Again, I want you guys to just take note of this word conjugate, because it's an important word that gets thrown around, and I wouldn't want you to trip up over it if you see it in an exam question or something. Okay, so like I was saying before, the main use case for these complex numbers, based on what we've done so far through GCSE and A-level maths, is to solve polynomials or polynomial equations. Every time, right, we got those nasty quadratics and we had to plug them into the quadratic formula, you'd hope that the determinant, which is b squared minus 4ac, is less than 0. Because if it was, then there's no solutions. And instead of sort of working with horrible surds and stuff, especially on a non-calculator paper, you could just write no solutions. Easy days, game over. But now you don't say there's no solutions. If this does happen to be negative, if this is negative, we can solve it now using complex numbers. So instead of saying no solutions, you say that solutions are imaginary. The good thing about imaginary solutions is that they always come in pairs, the complex conjugate pairs. So if one solution is a plus bi, the other solution will be a minus bi. If one solution is c plus di, the other solution will be c minus di. Just complex conjugate pairs. Okay, let's talk about Angard diagrams, Argand diagrams. I don't know what I just said. Argand diagrams. So we're all very familiar with graphs and just plotting xy coordinates and plotting lines and maybe even plotting quadratics and stuff. Argand diagrams work very similarly. Again, you just take a complex number in the form of a plus bi, right? Example, 2 plus 3i. You simply just plot the coordinates. Instead of x and y, the x-axis, remember this, the x-axis is always the real axis, the y-axis is the imaginary axis. So if you see a complex number a plus bi, you just plot ab like you would plot xy on an xy graph. So 2 plus 3i would be as shown here. This is 2, this is 3. 2 on the real, 3 on the imaginary. Now, what trips some people up with complex numbers is that I've just told you that most complex numbers will look like a plus bi, right? But actually, there's multiple ways that we can represent this a plus bi. In particular, A-level further math specification goes over 3 separate ways to represent complex numbers. One is a plus bi, which is just called the normal Cartesian form. Second is the modulus argument form, which is here. And the third one is the exponential form, which we'll cover later on in the video. But I want you to just keep this in mind. The same complex number can be represented in 3 different ways. Now let's see how do we actually get from an a plus bi looking number to the modulus argument form. As the name suggests, the modulus is the length of the vector. So in this case, let's go back to this example. If my actual complex number was 2 plus 3i, the length of it would be this red line here, how far it is from the origin, right? And the argument is nothing but the angle from the positive real axis. So not this angle, not this angle, it's always from the positive real axis, which is just the right hand side, let's say, of the x-axis in this case, right? This theta will always be the argument. So to find out the modulus argument form of a complex number, to find out the modulus, all you have to do is the square root of a squared plus b squared. Why? Because let's say this is a complex number 2, 3, I've plotted it. Well, as you can see, the length is clearly just going to be, this distance is 2, this distance is 3. Use Pythagoras, this is the right angle triangle. The square root of 2 squared plus 3 squared, right? And the argument, right, you can use the argument, or you can work out the argument using trigonometry as well. So in this case, theta, you're given the opposite angle is, the opposite side is 3, the adjacent is 2. So in this case, argument of z will be tan inverse of 3 over 2, whatever that works out to be. So remember this, if you're given a Cartesian complex number, to convert it into a modulus argument form is work out the modulus using Pythagoras, and then the argument, you often have to do trigonometry. And it's, in 99% of cases, it's just going to be inverse tan of the opposite of the adjacent. What you do have to be very, very cautious of is that what angle you're actually calculating. Because in this case, it's nice and easy. The theta's already making an angle with the positive right axis. In another case, let's say the complex number was here, right? And for argument's sake, let's just call this like 5 and 3, right? So this side's 5, this side's 3. Now you could very easily do tan inverse of 3 over 5 to get this theta, but that is not your argument at all. Your argument will be all of this. So whatever you get here, plus pi or plus 180 degrees, because the argument is always from the positive real axis. Okay, let's go through an example of this. I've already shown you an example, but another example to really get this through. So let's say we have a complex number w, which is minus 3 plus 3i. To find the modulus of it, all you have to do is just Pythagoras on the 2 times. So you do minus 3 squared plus 3 squared square rooted, which gives you 3 root 2. Modulus done. And I would highly suggest, especially if it's your first couple times doing this, every time you work out the argument, literally plot the point on an arcane diagram. It's not that hard. It will really help you visualize things. And you know the thing I was talking about? You can always make sure the angle you're measuring, is it from the positive real axis or is it not? Or do I need to add or subtract some combinations of pi? But yeah, in this case anyway, As you can see, because minus 3, 3 lies here, I've worked out this theta. But this theta is actually not the argument. In order to work out the argument, I have to do pi minus pi over 4, which is theta, to get 3 pi over 4, which is my argument, marked in green. This is a very common slip up. Don't fall for it. When you multiply and divide complex numbers, you saw how long it was, right? When you had to sort of do like the old expanding the brackets method in the Cartesian format. It's actually much easier to multiply and divide complex numbers when they're in their modulus argument form, because when you're multiplying it, as you can see here, you just multiply the moduluses together, and when you're dividing it, you just divide the moduluses. Done. Similarly, when you trying to work out the argument of z1 times z2, you just add the arguments of the individual complex numbers together, and when you're dividing them, then you subtract the arguments of the individual complex numbers together. Okay, so how do you actually write? I told you how to work out the modulus, I told you how to work out the argument. How is it actually represented? How is it actually written, right? So after you work out the modulus and argument, you can write a complex number that looked like a plus bi in the form of r brackets cos theta plus I sine theta. And as it says here, r is the modulus, and this theta, the cos theta and the sine theta, is going to be the argument, right? So let's take another example, 7 minus I. Use Pythagoras quickly, using the coefficients, so 7 and minus 1, to work out the modulus r, which is 5 root 2. I've plotted it, so I can see what angle I'm working out. Do inverse tan of 1 over 7 to get 0.142. So if you do work out this argument, it might look really odd, like, oh, I've got an argument of 0.142. It's perfectly fine, just plug it in. So the complex number 7 minus I in the modulus argument form will look like 5 root 2 brackets cos of minus 0.142 plus I sine of minus 0.142. Why is it minus? Well, because it's going the other way from the positive real axis. Cool. So let's talk about loci. Again, there can be some very challenging questions that do stem from this. But if you understand the basics and see what sort of questions there are on the market, like, you'll be able to do all of them, no problem. So what is loci? Loci is just any set of points that obey a certain rule. How do I find out loci? So the most common form of loci you'll get for complex numbers on the R-Garden diagram will be circular ones. Anything that's in the form of z minus z1, where z1 is your actual complex number, right? We'll see examples of this. Equals r will be a circle. The other loci you get is going to be lines. How do you know if it's a line or it's a half line specifically? When you have the argument given. The argument of z minus a complex number is theta. Let me just read the slide out to you because this is quite valuable information. So if you ever see anything in this format, z minus z1 equals r, it will be a circle. The center will be whatever the coefficients of z1 are. And the radius will be whatever this r is. Right? And if you see anything in this format, given the argument, then it's going to be simply starting. The half line is going to start at the point z1. It's going to go towards the positive real axis. So wherever the positive real axis is, it's always going to go towards it. It's always going to go towards the top right. And the angle is going to be theta. Let's see some examples of them drawn for better reference. So as I said, z minus some complex numbers. In this case, z1 is 2 minus 3i. Right? The center of the circle is simply 2 minus 3, and the radius is 2. So as you can see, the loci will be all of these points. that lie on the circumference in the circle. All of these lines, all of these points in the circumference of the circle will obey this rule, let's say. Okay, the other type of loci, the half line, z, the argument of z minus 2 minus 3, remember it's always minus. Again, common, if it's z plus, then just negate it. Make both your terms minus. But do not, please do not. If it's z plus, do not make a circle with that center. That's another really common metaphor. So z minus 2 minus 3 equals pi over 6. Now, the point is minus 2 minus 3 is going towards the positive real axis, which is here, right? And the angle is pi over 6. Now, the third type of loci, this is actually the most unique one, is when the loci will be a perpendicular bisector, as in a line that's going 90 degrees perpendicular through the middle of an imaginary line connecting 2 points. So if you have something like z minus z1, where this is your first complex number, or the first coordinate, and equals the modulus of z minus z2, right, which is your second complex coordinate, then the loci, or all of the points that will satisfy this particular rule, will be the perpendicular bisector, or the line that's making the perpendicular bisector. So in the example, chosen a very simple example for ease of explanation. One of our complex numbers is z minus 2, the other one is z minus 3i, right? So 2 and 3i, 2 points. The loci is simply, you sort of draw like an imaginary line connecting these 2 points. The perpendicular bisector to that imaginary connecting line is going to be the loci. Just to reiterate, these are the only 3 types of loci you're expected to draw and identify in all of complex numbers. Circles in this format, half lines in this format, and perpendicular bisectors, which will look something like this. Cool. So how do you work out the Cartesian equations of loci? These are some of the more challenging questions this topic has to offer. So I thought I'd make like a step-by-step guide on how to do it. So the very first thing to do is, all of these, right, assume that the locus point is some random point, right, which can be represented by x plus iy. It's just some random point. Then what you do is, you swap out x plus iy for z, you calculate the modulus, then you work out, use the inverse tan thing to work out the argument, and you simply rearrange. It's a lot easier to explain with an example. Let's go through it step by step. So if you were given this equation, this is clearly going to be a circular loci, right? So if you were given this and said, okay, can you please identify the Cartesian equation of all the loci that this equation will produce? Then you do swap out x plus iy in terms of z. You can rearrange this. You can group the non-imaginary terms together, the imaginary terms together, to get x minus 3 plus 4 brackets 4 plus y plus 4 I. So normally, remember, if we had 2 plus 3i, to work out the modulus, you just do the square root of 2 squared plus 3 squared, right? Same thing here. Square the real part, square the imaginary part, square root it to find the modulus. And you get this equation. Now, I started with root 5 because it's easier to deal with. You can just square both sides and you get a perfect equation for a circle. Right? This is just a circle centered at 3 minus 4, radius 5. And that's the Cartesian equation of the locus. Or the loci, sorry. Now, when you're trying to find the argument, same thing again, just swap out x plus iy for z. And because this is a y, this is a 1i, group them together, you can do the same thing. Do inverse tan on opposite, which is going to be the y-axis, divided by adjacent, which is going to be the x-axis. Right? So you can do not inverse tan of the argument right? Because technically it's tan minus 1 of y plus 1 over x. That's what it technically is. But it's actually the tan of the argument, we're taking inverse tan to the other side. Tan of whatever the argument is, pi over 6. Sorry, I keep accidentally tapping my iPad. Tan of the argument, pi over 6, which you can just whack in your calculator, give you an answer, minus root 3 over 3, is that. Then you can do some GCSE level rearranging to get to the equation of a straight line, which in this case just happens to be a really ugly looking equation. Root 3x plus 3i plus 3 equals 0. Okay, as I talked about earlier, this is the third way of representing complex numbers. The first way was Cartesian, a plus bi. Second way was modulus argument, which is r plus cos theta plus I sine theta, brackets in brackets, where theta is the argument, r is the modulus. It's really, really easy to convert from the modulus argument form to the exponential form. All you need is, again, the modulus in the argument. But instead of writing the cos and sine theta, you can just simply rewrite this as r e to the I theta. If you're interested, I won't fully go into it, but the reason behind this is the Maclaurin expansions for cos and sine, right? So maybe Google it after this video if you're interested, but they won't ask you to prove this or anything. You can literally just take this as it is, plug in the numbers, make your life easy. So, if you're given a complex number, like 2e to the 3 pi over 4i, how do we convert it back to what's familiar, a plus bi? Well, you can firstly convert it into the modulus argument form, right? And if you notice, like a lot of people fail to recognize this purely because it's so unusual. Normally it's like theta, normally it's like 2 theta, but it's just cos 3 pi over 4. You just whack this in your calculator, it literally gives out a real number, right? So you expand this into the modulus argument form, whack it into your calculator, and get something that looks like the Cartesian form, which in this case is just minus root 2 plus root 2i, right? I have to say, I think that the exponential form has to be the neatest way of representing complex numbers, because the modulus argument form and the Cartesian form just, I don't know, longer to write, look a bit ugly, so on and so forth. The two important proofs that you need to know in the subtopic, they sort of come up hiddenly. They can directly ask you for these proofs, but it's often sort of implicit knowledge, like something that you have to use as a part of a bigger question. It's good to go over them. As to how cos theta is the same as, this sign just means equivalent, as e to the I pi plus e to the minus I pi over 2. How does that work? Well, we can use the Euler's identity, which is e to the I theta equals cos theta plus I sine theta. Therefore, e to the minus I theta, or you can also this is just e to the I minus theta, essentially, right? Minus I theta is just, instead of theta, you just put minus theta in. And if you remember, because of the cos and sine graphs, right? Let me just quickly draw them. The cos graph is completely symmetrical about the y-axis, right? The sine graph is not. So cos of minus theta just equals to cos theta because it's completely symmetrical about the y-axis, whereas sine of minus theta equals minus sine theta. So this is basically what's implied here. So cos of minus theta just turns into cos theta, sine of minus theta turns into minus sine theta, right? Now if you do e to the I theta plus e to the minus I theta, then you get cos theta plus minus sine plus I sine theta plus cos theta minus I sine theta, which will eventually lead you back to where we started. Now, let's try and prove how sine 2 theta is equivalent to or is the same as 2 sine theta cos theta. So using the identities that sine theta is e to the I theta minus e to the I, again, you know how we've proved cos theta to be this here? You can use the exact same thing to prove sine theta as well. Okay? So using these two identities, you can say that 2 sine theta cos theta, instead of sine theta and cos theta, put long exponential forms in, right? Just straight off the bat, you can cancel out the 2's. So the 2 in the denominator, the 2 in the denominator here, you can cancel out this 2 with one of the 2's. So you're only left 1, 2 in the denominator. And then you're left with e to the I theta minus e to the minus I theta times by e to the I theta plus e to the minus I theta. And as you can see, I've just done it for you. It just expands to e to the 2I theta plus 1 minus e to the minus I theta over 2I. I realize I'm going through things a bit quickly. In the practice questions video, I will ensure that I'm working through the questions so you get a chance to sort of see through the steps and sort of connect the dots a bit more. This is meant to be a pure crash course, right? I'm literally just trying to stuff your brain with all the necessary knowledge required to even attempt complex numbers questions. Everything I'm saying now, I hope you're taking it in, but these things will start just making so much sense and clicking into place once you start doing practice questions. But yeah, this is how you prove these two identities. Coming on to the exam paper's probably favorite part of this entire topic, the amount of de Moivre theorem questions there are on the A-level papers. If you had to nail any one topic, obviously know all of it, do well on all of it. But if I had to like put my money on like what questions coming up, probably this one. All it is that if you have a complex number in the modulus argument form, as you have one here, and you put it to the power of n, to any power, it's simply the modulus to that power, and then the exponent just goes inside the bracket and is multiplied with the argument. So this is the exponent, you just multiply it with the argument, still inside the cos and inside the sign here. Okay? Because I didn't want to fit like de Moivre questions on these tiny PowerPoint slides, we're going to swap over to OneNote. There we go. I was worried for a second. I was like, oh, all that work has just disappeared on me, but it's still here. Okay? So in practice, for example, if you had a complex number, cos pi over 3 plus I sine pi over 3, all to the power of 4, right? Using de Moivre's, you could simplify this to cos 4 pi over 3, just literally just whack the literally just whack the 4 in there, right? Multiply the 4 to get 4 pi over 3. Then you can simplify this further into minus a half minus root 3 over 2i. Cool. Slightly more challenging question. If you're given a complex number in the Cartesian format, which is going to be a plus bi, something like minus root 3 plus I, and you're told to put it to a power, put it to an exponent. In this case, we're asked to find z to the power of minus 2. Right? It's so much easier to use de Moivre's instead of calculating it and actually sort of multiplying, expanding brackets and stuff. Just figure out the modulus argument form, use de Moivre's theorem, and then you can convert it back at the end. Which is exactly what I've done here. Tan minus 1, find the argument, pi over 6. Right? But because it's minus root 3 plus I know the actual argument is going to be pi minus pi over 6, which is going to be 5 pi over 6. Right? And the modulus, Pythagoras, root 3 squared plus 1 squared, which is just 2. So in modulus argument form, this looks like this. Cool. And now you just put it to the power minus 2. So you put 2 to the power minus 2, and you do 5 over 6 times minus 2, which just gives you minus 5 over 3. which is what you can see in here and in here. Simplify it using your calculator and you get an eighth plus root 3 over 8i. Cool. Okay, to the very last sort of subtopic of complex numbers, let's talk about the roots of unity. So there's a law of mathematics that states that the order of an equation is just a degree. It's like what the highest power is. So for example, in a quadratic like this, the order is 2. In a cubic, the order will be 3. It's just the highest power of x. Right? So the law of mathematics states that the equation of order n will have n solutions. Now you might be thinking, like before complex numbers, right? We thought that, okay, if the discriminant of the quadratic formula was negative, then no solutions. Wrong. There's imaginary solutions. Now there can be a mixture, a polynomial can have a mixture of real and imaginary solutions. So just as an example here, if you have a polynomial, this is meant to say z to the power 4 equals 1, right? You can actually, there's 2 real solutions, which are 1 and minus 1, but there's also 2 imaginary solutions. And as I said, imaginary solutions, if you just know one, the other has to be the complex conjugate of it, right? So in this case, the imaginary solutions are I and minus I. And we call all of these roots together. Roots is just another word for solution of a polynomial. We call all of these roots together the roots of unity. Okay? So, the general formula for getting these roots of unity, after you've worked one out, is if you have something like z to the power of n equals 1, there's going to be n solutions. Remember this, it has to be z to the n equals 1, right? So if it's not equal to 1, if it's equal 6, then divide both sides by 6. This only works if it's z to the n equal 1, right? Your solutions will be in the form of z equals e to the power of 2k pi I over n, where again, n is just the degree or the number of solutions, and k is going to be 0, 1, 2, and go all the way up to n. Cool? We'll see examples of this. Actually, let's see an example of this. So the question is, we have something like z to the power 4 equals 2 root 3 minus 2i, and we're supposed to solve the equation giving our answers in the form of r equals e to the power, in the exponential form. Like with anything, right? Firstly, work out the modulus. I'm ignoring the power of 4 for now. I'll add that back later. Don't forget to add that back. Just work out the modulus. Modulus is 4. Argument is minus pi over 6, right? So the general answer is going to be, like as we saw here, right? The general answer is just e 2k pi I over n, right? So the general answer is just going to be pi over 6 minus pi over 6, sorry, because that's the argument, plus 2k pi, right? I've just sort of times the numerator of this by 6, which is why it's 12k minus 1, taking the pi's common as well, right? So the general answer is going to be in this format, 12k minus 1 over 6 pi, where k is going to be 0, 1, 2, 3, right? But remember, this was for z. In the question, it's actually z to the 4, right? Which is why we now take z to the 4, right? So we got this is the general answer, and the modulus was 4, so 4e to the argument, the general argument, the generalized argument I said, right? Do a quarter of this, because it was z to the 4. So you do 4 to the power of a quarter. I don't know why I'm doing the fourth root. 4 to the power of a quarter, right? And then you also do this exponent e to the quarter, and because the laws are indices, the indices just multiply. So you're left with root 2 e to the 12k minus 1 over 24 pi. Now don't just leave it like that. You're expected to work out all the individual solutions. Don't leave it in terms of k. So as I said, now that you have the general argument, you can find the individual varying arguments by just plugging in 0, 1, 2, and 3. And I've done that here. This is when you plug in 0. Right? If you plug in 1, it's going to be 12 minus 1 over 24, 11 over 24. Plug in 2 is going to be 24 minus 1, 23 over 24. If you plug in 3, it's going to be 36 minus 1, 35 over 24. Now, often they'll try and catch you out by saying, make sure your arguments, right? Did I say W? No, I said Z. Arg Z is in the range of pi n minus pi. If they do say that, just convert this so that it is in the form. But this is the correct answer. Okay. Now, the very last type of question that you can get with regards to the roots of unity is this identity, which actually said that if you have any root of unity, right, then if you square it and if you cube it, they will also be roots because of the nature of complex numbers. So if you do 1 plus w, which is the root of unity, and then plus square all the way to, let's say if you have 4 roots of unity, if it was z to the power of 4, then you go to w cubed. Then 1 plus w squared plus w cubed will equal to 0, right? So just to quickly demonstrate how or why this works, I've taken, say that w is the 4th root of unity, that means it's z to the power of 4 solutions, right? Then for any root of unity, the question is asking us to show that 1 plus w squared plus w cubed equals 0. Now, there's 2 identities that are at play here. The first one being, remember the sum of the nth term of a geometric series, the formula, which is a 1 minus rn over 1 minus r. This is just a geometric series, right? Every time you're timesing by w times w times w times, it's just a geometric series, right? So you can do the summation of that, and because there's 4 terms, n is 4, so it becomes 1 minus w to the power of 4 over 1 minus w, right? And because the roots of unity are cyclical, because there's only 360 degrees, right? They form a quadrilateral on the Avogadro diagram. So if you go past 3, if you say w to the power of 4, you will just end up straight back at the first root of unity, which is 1 in this case, right? So w to the power of 4 is nothing but 1. So the numerator ends up being 1 minus 1 over 1 minus w equals 0 in the numerator, which ends up being 0. Hence proven. And that was it. That's the end of the slideshow. I hope you have much better knowledge of complex numbers than you did to start out this video. Remember, I will upload another video which will be just going through loads of different types of, in fact, every different type of practice question. All these topics I've covered, I'll make sure there's at least one question for every subtopic that we covered today, right? To give you great exposure. So watch that video, do plenty of practice questions on your own, and yeah, the best of luck. I hope I helped. If you want this PowerPoint slides or any personal consultation or anything like that, I'll leave my email in the description. Feel free to email me. I will respond to you. Alright, bye. Thank you.